Welcome all to my talk. I'm very happy that you all showed up digitally to listen to me. I want to thank the organizers for giving me the opportunity to well, explain to you some things that I'm enthusiastic about. In this talk, I will talk about q-analogues of several combinatorial things. And just to be on the safe side, I'm going to start with an introduction also to coding theory and q-analogues. I realize that this might be preaching to the choir, so maybe you already know all of this, but well, maybe you can just sit back and enjoy listening to something that you already know for a change. And after this introduction to coding and q-analogues, I will talk a bit more about how codes are related to designs and matroids and how we can find q-analogues of them. I can't see the chat, so please don't put any questions on it and leave them for later on. So to start with the coding theory part, traditionally speaking, this is the image that, well, I have in mind for coding theory. What you do is you have a digital message, you're going to send it to someone else via some channel, and a message arrives at the point where you want it to be. But of course, your channel is not perfect, it has some noise. And to make sure that your message isn't completely scrambled up and unreadable, we use error correcting codes. What does that mean? That means that before sending the message, we encode it, which actually means that we add some extra redundancy to it in such a way that if the channel messes up some of the message, the received word can still be corrected. And the idea of this is that before you send your message, you add some redundancy, such that in a sense, the code words you send, they look different. And after receiving, you can decode the received message to the code word that is closest. And that means that we need some mathematical way to say what it means to look different and be closest. Well, in mathematical terms, this is a metric, and there are several ways actually to do this. So the coding theory that we usually use consists of block codes, and block codes are vectors. So we decide that some of the vectors in fq to the n are in your code and some are not. Usually we take a linear subspace. And then what you do is you send a code word C. What is received is a vector y. And if no errors occur, then y is going to be equal to C and everyone is happy. In practice, this will not happen. There will be some noise, there will be some error, and mathematically we can say that what you receive is this vector y, which is equal to the send message E plus some error vector E. Now, when can we decode? That can we do if the weight of E, the Hamming weight, is not too big. That actually means there are not too many non-zero entries in E. And so this is this notion of closest and distance that I talked about before. It is the Hamming metric, and it says that the distance between vectors can be measured as the Hamming weight of their difference. And that actually just means that I'm going to take my two vectors and I look at all the positions where they differ. And the more positions they differ, the larger their distance is. Right. Well, these block codes, they've been around for a while and they are used in communication, but until a few decades ago, communication was usually just over one channel, right? You want to get a message from A to B and there's not really something in between. Whereas nowadays, we usually use networks to send messages. And that led to, well, a new sort of coding theory that's called network coding. And it comes from the following problem. So this is like the toy example that everyone in network coding starts with. It's called the butterfly network because, well, it looks like a butterfly if you have some imagination. And what's going on here? Well, there are two messages, A and B, that has to be sent to the two sinks below. Well, what can you do? A gets transported into the network. It goes straight down to the first sink, and the other one goes to the node in the middle. The node in the middle also receives B, and B get also sent down directly to the second sink. And the question is now, what are we going to do in the middle? Of course, you can send first A and then B, but this will be slow. So can't we find something a bit more fast? And the answer is yes. What you can do is you can have this node in the middle, take the sum of A and B and forward this, because then the sinks, one of them will receive A and A plus B and can calculate B, and the other will receive A plus B and B and can thus also recover A. And so the idea here for coding theory is that because you have this network structure and you don't want all this forwarding go one by one, you're just going to forward some linear combination of all the messages you receive. And then in the end, you do get all the messages, but it will be linear combinations of one another. And the way to think about this is, instead of sending vectors, we're actually sending rows of matrices. So these A and B here, they are now the rows of a matrix. And what happens with them during their traveling through the network is row operations. And that means that also the error correction, it can be done within this whole network structure. You don't have to do it like on all the short pieces between two nodes in a network. So a bit more formally, this is what happens. We call this a rank metric code, and a rank metric code is a bunch of matrices. What you send are rows of a matrix, and what you receive are also vectors, which are rows of a matrix. And if no errors occur, then Y will be the same as X, but with some column operations, with some row operations done in it. And these row operations are represented by this matrix A of full rank. And we know A from the network structure. Now, in practice, what happens is that you don't receive A times X, but you receive A prime times X plus Z. What happens is that your matrix A is not completely a full rank. It forgets to add some of the vectors while forwarding. And also there can be some error, which is the error that comes from all the separate communication between the nodes, but we collect it in one error matrix. And when can I decode successfully? Well, that's if the rank of A prime is not too small. So if I didn't lose too much of the information, and also if the error, if it doesn't have too high of a rank. And this too small and too big, you see that it depends on the rank. And formally, for these codes, we use the rank metric to tell the distance between two matrices. The distance between two matrices is equal to the rank of their difference. So instead of looking at the Hamming distance between vectors, we're now going to look at the rank distance between matrices. So where coding theory used to be sending vectors, in modern times for network coding, we use matrices. All right. I will tell you what these two types of codes have to do with each other. But before I tell you formally, I have to tell you what is a q-analogue, because it will turn out that one is the q-analogue of the other. Well, what is a q-analogue? It's roughly what happens if you generalize from a finite set to a finite vector space over the field Fq. So for example, for sets, I can count the number of sets of size k that are contained in the set of size n. This is the well-known binomial, n over k. And the q-analogue of that is we now count not sets, but spaces. And instead of size k, they are dimension k. And they are not inside a set, but inside a bigger space that doesn't have size n, but dimension n. And there you get the Gaussian binomial or the q binomial. And so this is an example of a q-analogue. Instead of dealing with sets and their size, we deal with dimensions. We deal with spaces and their dimension. In general, we can make the following, well, dictionary between sets and spaces. If you know what a lattice is, we go from the Boolean lattice to the subspace lattice. If you don't know any of the words here at the left, you can safely ignore them. Because what's happening is we go from a set to a space. The role of the element of a set will be played by a one-dimensional subspace of the space. The size of a set becomes the dimension of the space. We saw that already. The integer n also has a q-analogue. And so if we have n elements in our set, the q-analogue of that is that we have q to the n minus 1 divided by q minus 1, one-dimensional subspaces in our full space. For sets, if you want to see which are the elements that are inside two sets, we take the intersection. And we can do the same thing if we want to look at the one-dimensional subspaces that are in two spaces. We take the intersection of spaces. And if you want, like, the smallest set that contains two sets, we take the union of sets. And for spaces, if we want to take the smallest space that contains two spaces, we take the vector space sum. So this is a bit how we translate between sets and spaces. Now, if you want to go back from the q-analogue to, say, the normal case or the classical case, then actually what you do is you let q approach 1. Because if you like to say so, set theory is just linear algebra over the field with one element. As I mentioned before, codes in the rank metric can be viewed actually as a q-analogue of codes over the Hamming metric. And one way to see that is as follows. So suppose I have a block code, so a code that consists of vectors. Then for a code word, I can talk about its support. These are the coordinates that are not 0. And its Hamming weight, it is the size of the support. For the rank metric case, I'm considering a matrix M, which is an M times N matrix. And now its rank support is going to be the row space of this matrix. Well, why does that make sense? If I look at the support of a vector, I'm going to take all positions that correspond to non-zero elements, and I take together all these elements to form a subset. And what I do here is I take for the support all the, so to say, one-dimensional spaces that exist. And these one-dimensional spaces will be exactly the rows of your matrix. And I take them all together to get the row space. So instead of looking at all the coordinates that are non-zero, in the rank metric code, we look at the row space of your matrix. And the rank weight, which is also a weight but with an index r, is now the dimension of the support, because dimension is the q-analogue of size. And it turns out that the whole theory behind weights of code words can be taken in a q-analogue in this way. And so we can go from a block code to a rank metric code, and a lot of results about block codes can be transformed into results about rank metric codes. Well, this of course sounds very nice, and you would say, okay, so this is great, this q-analogue, we have our dictionary how to go from one to another, and now we can just, take a q-analogue of everything, all the results we have about block codes and get them for rank metric codes. But the thing is, it's not always that easy. And I want to explain to you why q-analogues are difficult by using two examples. The first one is, suppose I have a space that is a disjoint union of, suppose I have a set that is the disjoint union of two other sets. So the set E is the disjoint union of E1 and E2. Now, if I take a subset of E, and I call this A, then I can always sort of disassemble my subset into a disjoint union of A1 and A2, where A1 is in E1 and A2 is in E2. And this is something you can always do for sets. The thing is, you can't do this for vector spaces. If I have two vector spaces that are disjoint and I take their direct sum, which is the q-analogue of what happens here on the first line, then there are a lot of spaces contained in my sum that I can't write as the sum of something inside E1 in the sum and something inside of E2. Now you get a lot of extra vectors and also a lot of extra spaces. So every time you take a union in the set case, in the q-analogue, you have to take care that if you take the sum of two vector spaces, you end up with a lot of vectors and spaces that were neither in E1 nor in E2. And this complicates your proofs, right? Because every proof that for set theory uses this, you can't make a q-analogue of it because, well, the q-analogue is simply not true. Another problem with the q-analogue that is closely related to this is the problem of a complement. So suppose I take a subset of a set and I say, well, the complement is just all the elements that are not in my subset. Then what can I say? If I take any element in E in the big set, then it's either in A or it's in its complement, right? We also have this nice thing that if we intersect A with its complement, we get the empty set. And if we take the disjoint union of A with its complement, we get everything. Now, also this is not true in vector spaces. There's no notion of a complement that has all the things you have here. I mean, of course, we can say a one-dimensional space, it's either in A or it's not in A, and then we say it's in the complement. But if I look at all the one-dimensional spaces that are not in a given space, together they don't form a space. If I want them to form a space, and I want, for example, that their sum is everything, then I have a lot of options to do that, right? If I have a space inside a bigger space and I want to have another space such that the two add up to everything, then there's multiple options for this. If I wanted my complement to be well-defined, I could take the orthogonal complement, which is a very well-defined thing, and it inverses the ordering, and everyone is happy with that. But then it can happen, especially since we're over a finite field, that you know a space and its orthogonal complement intersect non-trivially. So also complements are something that make a q-analogue difficult. All right. So I hope that where we are now is that we've seen that coding theory traditionally did something with vectors and the Hamming metric. Rank metric codes do something with matrices and the rank metric. And the rank metric case is a q-analogue of the Hamming case. And a lot of results on the classical case, we want to make a q-analogue of that. However, finding a q-analogue is not always easy. So that's what we've seen so far. And I now wanted to talk a bit about some things in coding theory and combinatorics that someone might want to have a q-analogue of. And there are relations between codes and other combinatorial structures. And specifically, I will talk about designs and matroids. So there are quite some results for the classical case, like the set case and the Hamming metric, where codes, designs, and matroids are linked. And so it is, there's been a lot of research recently to find q-analogues of these kind of results, and I want to tell you some of them. I will leave out all the details, but well, I've given you a hint on where q-analogues can go wrong. So I hope you will believe that this was not all trivial to accomplish. So first of all, I'm going to tell you what a design is. So a design is a combinatorial structure, and it consists of a set V of elements that we call points. And then we take a family of subsets of V that all have the same size, K. We call them blocks. And every t-tuple of points is contained in exactly lambda blocks. And so these are all a lot of parameters to remember. You don't have to remember all of them. But the thing is, I take a set and a family of subsets that all have the same size and that have some nice property. That's basically what a design is. And so the q-analogue of this, and we call it a subspace design. Well, instead of having a set with a certain number of elements, we now have that V is a V-dimensional vector space over some finite field. We take a family of subspaces of dimension k, and that's the q-analogue of taking subsets of size k. We call them blocks as well. And now it's the case that every t-dimensional subspace is contained in exactly lambda blocks. And so you see that all the properties of a design, they carry over to the subspace design. We just take a q-analogue of this definition. Well, just in case you never saw a design before, this is everyone's favorite example. Well, maybe not everyone's, but for a lot of people, it's the Fano plane. It's also geometry, of course, but it is also a design. It consists of 7 points, and it has blocks, which are the lines of the Fano plane. And if I take these 7 blocks, then what is the case? I have 7 points. I take blocks of size 3, and every tuple of 2 points, so every pair of points is in 1 block. And so here it just says that every 2 points are on a unique line, which is of course what makes a projective geometry. But you can also see it in the picture, right? If I take any 2 points, like 7 and 2, there's a unique line that has 6 with it, where these 2 points are in. The thing is, we don't know if there exists a q-analogue of the Fano plane, which is slightly embarrassing because the parameters are so small. But what you would want to have for the q-analogue of a Fano plane, it is a 7-dimensional space. And then I take a bunch of 3-dimensional spaces in such a way that every 2-dimensional space is in exactly one of the 3-dimensional spaces. Now, the reason why we don't have it is because it's incredibly big. Even if you would do this over the binary field, I think the number of blocks you need, well, here you needed 7 blocks, but for the q-analogue of the Fano plane, you would need 381. And so it's no longer possible to just try everything and see what it works out. It's too big for that, and so you need more clever ways to find something like that. In general, we don't really have a lot of examples of subspace designs exactly for that reason, because they're so big, so we can't just hunt for them by a computer. Of course, there are some smart tricks that you can do, but I won't talk about that. Now, what's the deal with designs and their links to codes? Well, there is a famous and well-celebrated theorem by Asmus and Madsen, already from the 60s, that says, if I have a linear block code and some nice properties, I can get a design out of it. Well, how does that work? If I look at my code and I look at its dual, I won't define what it is. You have to believe me that a dual object exists. If this dual has not a lot of different weights, then if I look at the supports of the code words that are close to the minimum possible weight, like in my original code, then these supports form a design. Let me explain that with an example. So here is a generator matrix of the extended Hamming code. That means that my code consists of all linear combinations of the rows of this matrix. So there are 16 vectors. One of them has weight 8, which is the all 1 vector, and the other, there's of course the 0 vector that has weight 0, and all the other ones, they all have weight 4. You can check that if you just write all of them down. And that means that we indeed have something that has only a few weights. This thing is self-dual, so it's enough that my code itself has only a few weights. And that means that if I would take all the 14 words of weight 4, so 3 of them you can already see here, they are the second, third, and fourth row of the matrix. And then if I look at all the positions where the ones are, then this support, the positions of the ones, it will give me a design on 8 points, and I take blocks of length of size 4, and then every 2 points is in exactly one of the blocks. And so that means that if I would take 2 positions in the code, I can always find exactly one code word that has ones on both these positions. So this hopefully gives us an idea of how to get from a code to a design. Now, a few years ago, Emer Byrne and Alberto Ravagnani made a q-analogue of this result. They start with a linear rank metric code. It also has some technical conditions, and I mainly wrote this line to err on the safe side. But the rest of the statement is as we had before. You're going to look at the dual of the code that we can also define for rank metric codes. If it has few weights, then if I look at the code itself and I take the code words of a weight close to the minimum weight, then they form the blocks of a subspace design. So this is actually the kind of q-analogue that you would like to see. I have a theorem about the classical case. You can get a design from a code, and the q-analogue, it looks exactly the same. So this is how we can get designs from codes. We can also get designs from matroids. And first I have to tell you what is a matroid. A matroid is actually a kind of a generalization of a graph or of a matrix. If you like, I'll give an example on the next slide. But basically what it is a finite set, and it has a rank function on it. And this rank function just says, well, if I take any subspace of my subset of my set E, then I can assign a rank to it, and this rank function has certain nice properties. Please forget about these nice properties. You don't have to recall them. I just put them here to show that they exist, and they're, well, not that difficult to handle. And the thing is, if I have a linear block code, then I get a matroid. The ground set is the set of columns of a generator matrix. And now if I want to have the rank of a subset, I just take the rank of the submatrix that is formed by the columns of A. So the reason that this matroid has a rank function that is called that way actually comes from linear algebra. So this actually tells us that linear block codes are a special case of matroids. So here are some examples of matroids. This is a matroid on 5 elements. And how can you see what is the rank? Well, for example, if I want to have the rank of the first 3 columns, I'm going to take the submatrix formed by that, and it has rank 2, and so that's the rank of this set. If I would take everything, I get rank 3, and if I would take, for example, the third and the fourth, I get rank 2 because the submatrix has rank 2, etc. Matroids also come from graphs, and here you see a picture that's actually the same matroid as that I said before. But now what you're going to do is a rank so the elements are the edges of the graph, and the rank of a subset is the size of the largest spanning tree. So for example, if I take A, B, and C, well, they form a cycle, and the largest spanning tree inside has size 2. So I say that the set ABC has rank 2. And just like that, the first 3 vectors, column vectors here also have rank 2. And you can also see that ADE is dependent, just like A, D, and E are dependent above. And so you can also start with a graph and then get a matrix, a matroid out of it. However, most matroids don't come from a matrix or a graph, so it's really a more abstract notion. So we see that codes are a special case of matroids, and we want to make a q-analogue of that. Well, for that, we need to have a q-analogue of both codes and matroids. We already saw what is the q-analogue of a code. It is a rank metric code. And so we need the q-analogue of a matroid. And this is like a straightforward q-analogue of the definition that I just showed. Now we have a function that assigns to any subspace a number in such a way that this rank function satisfies certain properties. And these are exactly the properties that we just had, only we replaced size by dimension, and we replaced union by vector space sum. And you can prove that a rank metric code, actually an FQM linear rank metric code, if you don't know exactly what it is, it's a special case, that gives you a q-matroid. So it's not just that we can make a q-analogue of our definition. There's also actually examples from it, because rank metric codes gives us q-matroids. However, not all q-matroids come from rank metric codes. So it's also an interesting thing to study in its own right. So now that we know a bit about matroids and codes, and we've seen that codes are actually a special case of matroids, the following makes sense. This Asmuth-Madsen theorem that says codes give designs can actually be generalized from block codes to matroids. So you can't just have this result starting from a code, but also if you start from a more general class of matroids. And this was done by Royal and Shiramoto in 2009. And they basically gave away for, well, they gave a theorem that says, suppose we have a matroid and it satisfies certain conditions that really look like the conditions in the Asmuth-Madsen theorem, but translated to the matroid case, then you can get designs out of it. And a recent result that I had with Imer Byrne and Michela Seria and Sorina Ionica is that this generalization of the Asmuth-Madsen theorem also has a q-analogue. And so this theorem that we had, that rank metric codes give designs, you can generalize it by saying that q polymatroids give designs. Now Heidi will tell you exactly what is a polymatroid, I think. It's slightly more general than a matroid. So, but of course you have to work a bit for these theorems, because I mean the theorems may look like a direct q-analogue, the proofs are often not. So this is a way where matroids can give designs, and there's a second way in which matroids can give designs, and for that I have to tell you a bit more about matroids. Namely, so we know that a matroid, it's a finite set with a rank function on it, but there are also some special subspaces of this finite set. And I will give you 3 of them. The first is an independent set. That's a subspace where the rank is equal to the cardinality. If a set is not independent, it's dependent. And if it's a minimal dependent subset, we call it a circuit. This is a term that comes from graph theory. If you have a cycle in a graph, then you have that its maximal spanning set is actually 1 less than the total number of edges. And the third thing is a flat. And you can see a flat as sort of the span of some elements. It's a subset such that if you add any other elements to your subset, then the rank will go up. So you can make a flat by taking a subset and adding as many elements to it without having the rank blow up. So it's a bit like taking a span. So the terminology also comes from geometry. We can actually show that matroids are completely determined by their independent sets, circuits, and flats. Now, if we have a special type of matroid called a perfect matroid design, which is a terrible name, but well, we have to deal with it. It's a matroid where all the flats of the same rank also have the same size. And there are several examples of them, and one of them is a design where lambda is equal to 1, which is also called a Steiner system. So, and there is a theorem from 1970 that says if we have such a perfect matroid design, then we can make designs out of it by seeing all flats of the same cardinality, all independent sets of the same cardinality, or all circuits of the same cardinality. So the interesting thing here is that you start with a matroid and you look at a bunch of sets that really come from a matroid, like all flats of a certain size, all independent sets of a certain size, all circuits of a certain size. And this will be the blocks of a design. And that's a very nice result. It was actually used to find new designs as well. And what you can do is, of course, you need sort of an input for this in order to get all these designs. And so what you can do is you can start with this special design, with this Steiner system, and then it will give you new designs. However, these new designs, you really need like a matroid theory structure in between to get this. So you can start with a design and get other designs out of it, but you really need to do that via matroid theory. So there is a q-analogue of this thing as well. Oh, I first wanted to give you an example. So here's our design that we saw before, the Fano plane. Now, if I view this as a matroid and I say, well, the rank, it is, well, the dimension of the span of these points from geometry point of view, then you get, for example, that if I take the pairs of points, that they will also form a design. It's not a very interesting design because obviously every 2 points is in one block, because I just made all, you know, pairs of points, I made them blocks. So it's not a very interesting thing. But if I take, for example, 3 points that are not on a line, and I take all the possibilities for 3 points that are not on a line, then it will form a design. I will have again that every 2 elements are in the same number of these blocks. And that's because for every 2 points I see here, I can pick 4 other points to add with them in such a way that you don't end up with a line. And you can do something similar with the flats, but it doesn't give you a very interesting design. However, circuits, they do give you an interesting design. If you look, for example, at the points where you have 4 points and no 3 are on a line, that's a circuit from a matroid point of view. And it will, if I take all these circuits, then I will get a design out of it. Well, unfortunately, I can't do the q-analogue of this because there's no q-analogue of the Fano plane. However, there is a q-analogue of the theorem. It uses a q-PMD, which is the q-analogue that you expect. It's a q-matroid where all flats of the same rank have the same dimension. So instead of having the same cardinality, they now have the same dimension. And an example of this is a subspace design with lambda equal to 1, and that's also called a q-Steiner system. We managed to prove that if you start with a q-Steiner system and you view it as a q-PMD, then you can get new subspace designs out of it by looking at all flats of a given dimension, all independent spaces of a given dimension, or all circuits of a given dimension. And well, we don't really have a lot of q-Steiner systems to sort of use as input for this theorem, but the one that we have, it did give us a new design. So we were very happy with that. We also tried to put in, you know, the q-Fano plane, of which we don't know it exists, and we were hoping that this theorem would give us a design of which we already knew that it didn't exist, but that was not the case. I mean, one could hope, but it didn't. So this was a q-analogue of the theorem we saw before, that you can use a matroid to find a design. So I hope to have given you some idea of how codes and designs and matroids are related, and how I can get designs from codes and designs from matroids in different ways, and that they also have a q-analogue. There are several other relations that I didn't mention here, but that are also waiting for q-analogues in these structures. So there's a lot of things to do. And I hope that, well, you like these things and maybe work on some of the things, work on some q-analogues of these things with us. So thank you for your attention. I'm available for questions at the end of this session, and also tomorrow before the last research session.